There's a lot of talk about nuclear technology, what with Iran and Fukushima and green energy being thrown around in the news every day. But how do we even make nuclear fuel, guys? Howdy there, atomic children. Trace here for D-News. Despite the controversy they often raise, nuclear power plants are a huge source of our energy. The Environmental Protection Agency says nuclear power accounts for about 20% of electricity production in the U.S. One of the reasons why is because it's the most efficient means of extracting energy from a fuel source, about 8,000 times more efficient than coal or oil. According to the Nuclear Energy Institute, a fingertip-sized pellet of nuclear fuel contains as much energy as 17,000 cubic feet of natural gas, 1,780 pounds of coal, or 149 gallons of oil. Nuclear energy comes in two flavors, fusion or fission. Fusion is when two hydrogen atoms fuse. This happens in stars. And fission is when large, heavy atoms are broken apart. Both release energy, and both have pros and cons, but so far, we've only figured out nuclear fission. So when I say fuel, I'm talking about fuel for nuclear fission. Nuclear fuel is commonly referred to in the news as highly enriched uranium, but getting it to that point requires a lot of effort. In 1941, Enrico Fermi created the very first controlled nuclear chain reaction using a small amount of uranium-235. And since then, we've gotten much better at taking uranium and creating usable fuel from it. Uranium ore is most commonly mined in Canada, Australia, Niger, Russia, Kazakhstan, and Namibia, though it's not that rare. It's 40 times more prevalent than silver in the Earth's crust. Once drilled or dug out of the ground, the uranium atoms are mixed in with the surrounding minerals, so it has to be processed, and this involves some pretty intense chemistry. First, the ore is crushed and then heated to dry out carbon content, like clay, so that it can be washed away. That slurry of ore and water is leached with sulfuric acid. This process causes the uranium atoms to bond with the sulfur and oxygen, forming uranium oxide liquid. To get it to that yellow powder that we recognize from movies and television, the uranium is pulled out of solution using ammonia. This yellow cake uranium is put into barrels and shipped off to be purified even more. At this point, the uranium isn't super radioactive yet. If you stood 1 meter from a barrel full of U-308, you would get no more radiation than from the cosmic rays that hit passengers on a commercial airplane. This uranium still needs to then be enriched before it can be used in power generation. That yellow cake uranium is 99.3% uranium-238 and only 0.7% uranium-235. To make the fuel, scientists need that uranium-235 isotope. This is where the now famous nuclear centrifuges come in. If you watch the news, then you know Iran is developing a nuclear program. Whether for energy or for weaponry, I'll leave that to the experts. But they use centrifuges to enrich their uranium. As things go forward from here, it gets more dangerous and more radioactive. So the engineering has to be very precise or people can die. Firstly, they take the yellow cake uranium and they turn it into a gas by creating a reaction with fluorine. The resulting uranium hexafluoride gas is even more pure than yellow cake and ready to go in a centrifuge. A centrifuge is a giant spinning container designed to use physics in order to separate materials. When you donate plasma, for example, doctors draw the blood and then spin it in a centrifuge. During the spinning, centrifugal or center-fleeing forces cause the heavier red blood cells to come out of solution and collect as far from the center as possible. Lighter plasma stays nearer the inside. In the case of uranium, it's the same. The heavier U-238 isotopes get thrown outward, allowing the lighter U-235 to stay closer to the middle of the centrifuge. It's not as good as blood because there's only a 1% difference in mass, so it has to be spun again and again and again in centrifuge after centrifuge, thousands of times. Eventually, the gas in the middle of the centrifuge gets more and more concentrated or enriched. The gas is more U-235. Once the fuel is 5% U-235, 95% U-238, it's suitable for some nuclear reactors. Others require as high as 20% U-235. But that's nowhere near enriched enough for nuclear weapons, which can require as high as 90% uranium-235. Once it's reached the desired enrichment for the type of power plant you want to run, the enriched uranium hexafluoride has to be turned back into a solid by adding calcium. The calcium and the fluoride react, creating a salt, leaving behind only uranium oxide, which is then heated to 1400 C and extruded into tiny ceramic pellets. Those uranium pellets are in turn put into rods, and then hundreds of thousands of those rods can be placed in various configurations inside of a nuclear power plant. Easy. When we talk about nuclear energy programs in other countries, world leaders get nervous. And now you know that process. So can you see why? The massive centrifuges used to make nuclear fuel are the same ones that could be used to create weapons-grade uranium. It requires a lot of technical and chemical knowledge to get to that point, but in the end, it's dig uranium out, clean it up, and spin it. Nuclear energy continues to be a controversial choice for powering the future, and its connection to nuclear weapons is pretty clear. But how do you feel about nuclear energy? You can tell us down in the comments. Plus, now that you know what those pesky centrifuges are for, you can watch this handsome devil break down which countries use their nuclear fuel and actually creating nuclear weapons over on TestTube. These countries refused to sign the treaty before it was put into effect in 1970, primarily because it capped the number of countries who were allowed to have nuclear weapons at 5. The 5 countries that already had them. Subscribe, like, love, hugs. Thanks a lot for watching. We'll see you next time.